Welcome to a lesson with Dr. Powell. Let's take a look at how we can compute the derivative of the inverse function of sine inverse of x, using a limit. All right, and the knowledge that the derivative of sine of x is cosine x. Okay, and we're going to start by looking at a limit that gives us the derivative of sine of x, and we already know what the value of the limit is. It's cosine x. And we're going to have a limit. This limit, we're going to get 2 points close together on the curve of sine x, x plus h, so the x value of x plus h, and x. 2x values close together, they come together in a limit as h approaches 0. And we're looking at the slope between the 2 points on the curve. And as those 2 points move close together, the slope between them becomes the slope of the tangent line, which is cosine x. So we plug in x plus h into the function sine x to get the y value there on the graph of sine x. And we plug in x into sine. Great. We have rise over run, so y difference over x difference. So sine of x plus h minus sine of x, all over the run, x plus h minus x, which is just h, but I'm going to write it down as x plus h minus x. We know this limit is equal to cosine. Now we're going to use a fact that we know that sine inverse is the inverse of sine, and keep in mind it's only the inverse of sine restricted to a particular interval. Sine of x on its own really doesn't have an inverse function because it's periodic and doesn't pass the horizontal line test, but you have to restrict it before you find its inverse. So really it's the inverse of a restricted version of sine. So really you can keep that in mind here when I say sine inverse. But take a looking at x plus h and x, we can rewrite these guys using the fact that this is an inverse to sine in the following way. We could think about this as being the limit as h approaches 0, sine of x plus h minus sine of x all over sine inverse of sine of x plus h, ooh, right there, minus sine inverse of sine of x. All right. So, thinking of this sign that I'm using all around as being the sign restricted, then these exactly cancel each other everywhere. So I can freely do that. Wow, how is this useful? It just looks like it overcomplicates things, right? But actually, it's kind of nice if you think about substituting for things. I mean, this guy right here, sine of x plus h, think of that whole quantity as being like an a, and this whole thing as being like a w. This guy right here is being like an a, and that being like a w. This looks like the reciprocal of sine inverse of a minus sine inverse of w, all over a minus w. That looks like something that will actually limit to the derivative of sine inverse of a. That's what we want. So assuming that, let's give a name for this, assume that g of x is equal to sine inverse of a, then this thing right here will limit to, as a approaches w, right? A approaches w when h goes to 0. So as h goes to 0, this thing will look like that. A will go to w. So yes, so as h goes to 0, this part really will behave as a is going to w, which gives you the slope of the inverse function, sine inverse of x, where, well, a is going to w, so it's right at the point w, right? The input into that, so this is g prime of w, plugging w into the derivative of sine inverse. So, wow, this whole limit then is the reciprocal of that. this is the reciprocal of this, right? So this whole thing will actually limit to 1 over g prime of w. This is a minus w over sine inverse of a minus sine inverse of w, reciprocal of this. So we get that cosine of x is equal to that. Take reciprocals of both sides, and we end up getting that g prime of w is equal to 1 over cosine. Well, how in the world do we work with that? We want to function in terms of w to find the formula for g. How do you, well, what is w? W is sine x. Can we write cosine x in terms of sine x? If we think about a defining triangle for sine and cosine, like if the hypotenuse is length 1, then this side, and this is x, then this side length is cosine x, this side length is sine x. Pythagorean theorem will do the trick. Or just knowing that we have, these are coordinates on the unit circle all the way around, and it satisfies the property that this squared plus that squared is equal to 1 all the way around, no matter if we're over there or there, wherever else we are. So, but of course, x is restricted anyway because we're dealing with sine inverse. So, and the fact that, and we have fun restrictions anyway going on with that. But anyhow, taking a look at this, be a little bit careful. Oh, I wrote down, yeah, you notice these x's and w's and everything, they don't really correlate, do they? Because, I mean, x here is behaving like an angle when I plug it into these guys, and that's okay. Up here, it's not behaving like an angle, it's a ratio, because sine inverse, it like flip-flops what input and output are. Like you plug in a ratio and you output an angle. But in any case, let's just look at this right here, abusive notation perhaps. But we have cosine x, sine x, 1x, and you have this Pythagorean theorem. You can rewrite, you can think of cosine as being, let's say sine was w, right? And what we're interested in is rewriting cosine x in terms of w, and that's okay because this w is actually going to correspond to really what this guy is, what we're really plugging into sine inverse. So maybe I really should write sine inverse of w. Okay. All right. So how do you rewrite this using the Pythagorean theorem? Well, you think w squared plus this guy squared is equal to 1. And if we solve that, we'll end up getting the square root of 1 minus the quantity w squared. Right? 1 minus w squared. This is the same thing as cosine x. If you want, we could work that out. Cosine x quantity squared plus w squared is equal to 1. So you have 1 minus w squared over there, and to square root it. Of course, I guess we should keep track of the plus or minus there when we solve. But realize that how things are restricted with sine, we're going to be in, so with things restricted with sine right here, so cosine x, so the output of where at the angle, so if this x is referring to angle, the angle is between negative pi halves and pi halves. And notice that when we're in that range, the cosine x output is going to be positive anyhow. So we're going to be picking a positive square root when we do the plus or minus in the computation. Hey, that's pretty good. That's it. That's the derivative, g prime of w. Of course, we could write it with an x, but w is fine, right? Derivative of sine inverse of w is 1 over the square root of quantity 1 minus w squared. Okay, so that is the derivative computation, and we got it by a limit by just thinking about this fraction here, and thinking about these input things as really being, applying the inverse to the function there, them canceling out, noticing that it's really just the same as this guy flip-flopped. But notice where we're focusing on, what we're plugging into the inverse function is the output of the sine function, So anyhow, it works. It's great. We made the computation. There it is. So if you ever see this function floating around, there's its derivative right there. Thanks for watching.